for linear antennas of n isotropic sources. Linear antenna of n isotropic sources. So what you exactly do here is, it is a linear array, linear antenna array. There is an array here. That means, there are many antennas. So this array of antennas are placed, that is n number of antennas are placed, and you need to find out the electric field intensity of this n number of antennas. So if I draw the normal figure of this linear antennas, you have n number of sources. So I'll consider the first source to be at the origin, and there is a second source. Again, there is third source, fourth source, and it continues. There are n number of sources, each separated by a distance d. 1 and 2 separated by distance d. Similarly, 2 and 3, and 3 and 4. And you have to find out the path difference. Similarly, there is a point P somewhere, and you will be trying to reach that point. Similarly, one will also be trying to reach the point. You have angle phi, as well as you have 2 dash, where you will be finding out the path difference. Now here, you will consider a linear array as one, which means linear array is the one where sources are placed at equal distance from one another. You have n number of sources. This n number of sources are placed at equidistance from one another. So we consider here a linear uniform array of n isotropic sources. Now when I say uniform array is the one in which all the sources are supplied with equal amplitude and phase. So uniform array is nothing but you have n isotropic sources. These all sources will have equal amplitude as well as equal phase. So that is called as a uniform array. Now this with equal magnitudes or current or with phase, it will increase progressively as your sources increases. Now if you consider source 2, we know source 1, there is no phase angle, that is xi, because it is in the origin. It will be having xi is equal to 0 here. Whereas source 2 will have a form that is xi. Similarly, source 3 will have 2 xi. Similarly, source 4 will have 3 xi, and it will continue. So each of the phase and magnitude will increase progressively for each sources. Source 2 at an angle xi with respect to source 1. Source 3 at an angle 2 xi with respect to source 2. Similarly, or source 1. Similarly, source 4 at an angle 3 xi with respect to source 1. And it continues. Now, all the sources are supplied with a magnitude of current. So you have to consider a amplitude for all the sources. We will consider the amplitude of all source as E0. Now you have to write the total pattern equation. Starting from the first source, we have considered it as E0. So we'll write it as E0 as the magnitude of first source. And e to the power j. It is in the origin. So this will be 0 plus second source E0 e to the power j. The phase angle for the second source is xi. So it will be j xi plus E0 e to the power j 2 xi, and it will go on continuing. What will be the last nth source equation? E0 e to the power j n xi or n minus 1 xi? See the first pattern, you have j0. It's not j like you considered xi here. So instead of n, the last pattern will be n minus 1 xi. From this now, take out E0 common. So you will be left out with e to the power j0 is 1 plus e to the power j xi plus e to the power 2 j xi. until e to the power j n minus 1 xi. Now, if all the sources, I'll consider all the sources are supplied with equal magnitude, if your E naught is equal to 1, which means all the sources are having equal amplitudes. In that case, again, your E will become 1 plus e to the power j xi plus e to the power 2 j xi until plus e to the power j n minus 1 xi. Consider this as equation 1. Now, to this equation, multiply with e power j xi on both sides. So you'll get the equation as e to the power j xi, which is equal to, multiply it. So 1 into e to the power j xi will be e to the power j xi. This will be e to the power 2 j xi plus e to the power 3 j xi until you have here, if you split it and write this particular term, it will be e to the power n xi into e to the power minus j xi. So you are multiplying with e to the power j xi. This e to the power j xi and the e to the power minus j xi gets cancelled. You will be left out with e to the power j n xi, which is considered second equation. Now, equation 1 minus equation 2. So you will be getting the equation as E minus, or that is the first E minus e to the power j xi, this term and this term. Left hand side, I'm subtracting it. What will be the remaining in the right hand side? If you subtract equation 1 and equation 2, the remaining term in the right hand side. So you have e to the power j xi minus e to the power j xi. This gets cancelled. This gets cancelled. What will be the remaining term? What are we? 1 minus or plus?
E to the power minus j xi.
1 minus e to the power j n xi. So now here take out e common. It will be 1 minus e to the power j xi, which is equal to 1 minus e to the power j n xi. I'll explain you once again. Consider linear antennas spaced at a distance d from each other, and each source will have their own phase angles. This is a 0, source 1 because of origin. This will be xi, third source 2 xi, fourth source 3 xi, and it continues. Write the electric field intensity equation. Consider the equal amplitude for all, which is E naught e to the power j0, j xi, 2 xi, and till n minus 1 j xi. Take out E naught common. Then consider if E naught is equal to 1, equal amplitude for all the sources. You will get this equation, make it as equation 1. To the same equation, multiply with e power j xi on both the sides. You will just multiply 1 into e power j xi, 2 j xi. It will increment by 1. So you'll have the last term e to the power j n xi. Equation 1 minus 2, you will get the rest, all the terms gets cancelled because before n you will have n minus 1. So all the terms gets cancelled and you will be only left with 1 minus e to the power j n xi. From here, take out e common. You have 1 minus e to the power j xi, which is equal to 1 minus e to the power j n xi. Is that clear till here?
Yes, ma'am.
Here the screen. Now, you have in the left hand side E, which is equal to, this is 1 minus e to the power j n xi divided by, I'll bring the left hand side which you have taken common to the denominator. So 1 minus e to the power j xi. From this, I'll take out e to the power j n xi by 2. What will be the remaining term here? If I take out e to the power j n xi by 2 in the numerator, you need to get 1. So what I have to multiply, or what will be the equation here?
E to the power minus j n xi.
Correct. E to the power minus j psi by 2. What will be the term which is remaining here? The same term, right? E to the power j n psi by 2 plus e to the power j n psi by 2 will be 2j n psi by 2. 2 gets cancelled. Whatever you take, the same term, negative, or if it is positive, it will be positive remaining here. So it is e to the power j n psi by 2. Divide it. Take out from the denominator e to the power j psi by 2. So what is remaining in the denominator now?
E to the power minus G psi by 2.
Minus
E to the power J psi by 2.
e to the power j psi by 2. Now you can see here, we need to take the negative term outside so that we can apply the formula of sine or cos. So I'll just take out the negative from both the sides. So it is minus e to the power j n psi by 2 divided by minus e to the power j psi by 2, which will be e to the power j n psi by 2 minus e to the power minus j n psi by 2 divided by e to the power j psi by 2 minus e to the power minus j psi by 2. Which formula I can apply here, or what will be the formula here? It is in terms of e to the power j theta minus e to the power minus j theta. So which one? Sine or cos?
Sine.
Sine. So it will be
2 sine theta.
2 sine theta or 2j sine theta. So if I apply it here, it will be 2j sine theta will take the form n psi by 2 divided by again 2j sine theta will take the form psi by 2. So here 2j gets cancelled. You will be left out with E is equal to e to the power j psi by 2. I'll bring the numerator to the, denominator to the numerator. So actually you will have e to the power n psi by 2, e to the power minus j psi by 2. And this term will be sine n psi by 2 divided by sine psi by 2. Again, if you write this, take out psi by 2 as common. You will have n minus 1 sine n psi by 2 divided by sine psi by 2. And here I'll consider this as an angle, that is phase n minus 1 into psi by 2 as eta. So I can write it as E is equal to e to the power j with this term sine n psi by 2 divided by sine psi by 2. If your angle is 0, then you will be left out with only sine n psi by 2 by sine psi by 2. Now here you have to apply the condition of limit now. What is actually, when you apply limit, just a minute. What is actually limit theta tends to 0, sine theta by theta value?
1.
It is 1. So you know the limit, it generally says the theta value, if it is tending to 0, sine theta by theta, or it is x by sine x by x, or x tending to 0, it is taking the value as 1. So here to this equation, if we take the phase as 0, so it will be E is equal to sine n psi by 2 divided by sine psi by 2, where we consider this as equation 3. Now we apply the limit condition, that is sine theta by theta is equal to 1, which means that in order to find the maximum value of your electric field from this equation, we have to convert this equation into a form of limit theta tends to 0 sine theta by theta. Now, if this term has to take a form of, or this equation has to take the form of limit, how can you write this E maxima or the electric field in terms of limit? It has to go to this form. both. So how you can write it? I should write in the form of, or this is the limit xi tending to 0. So numerator and denominator should be divided by same term when you apply the limit to get sine theta by theta. So either it has to be n xi by 2 or it has to be xi by 2. See, you have theta here. Here you have theta. You have to get it in this form. And since n is considered for the linear array, n isotropic sources, we take the form of theta as n xi by 2. So you will be writing it in this form, considering numerator sine n xi by 2 divided by n xi by 2, that is divided by sine xi by 2 divided by n xi by 2. So to bring it to the limit form, you are dividing both the equations by, or the numerator and denominator by n xi by 2, because we are finding it for n linear antennas, sorry, n isotropic sources of linear antenna. So you have to divide it by n xi by 2. So now you can see the equation. So this equation is giving you the limit form. If you consider here, this equation is giving you the same limit, which is equal to 1. So you will be left out with E max is equal to, what is the value remaining if these limits goes to 1?
N.
It is n. So E will give you the maximum value n. We know that E normalization is equal to E by E max, that is value divided by maxima. But we know that E value is from equation 3, sine n xi by 2 by sine xi by 2, and you have divided by n, which I'll write it here. So this equation is the one which you have to derive. So this equation says that, or this equation name is called as array factor, which is again very important in terms of your derivation. So it's an array factor where you are going to find out the normalization of the electric field intensity of the linear antennas when you consider n number of isotropic sources. So here you have to remember value of electric field pattern in any direction of theta is maximum only for xi is equal to 0. Any confusion in derivation? Or you want me to explain any of the part? If not, we'll move to the next. Now here, in the non-isotropic sources, I told you earlier, there are again 4 cases to be derived in non-isotropic sources. And what actually happens is you get confused with isotropic cases and non-isotropic cases. So remember, here it is directly you're writing the cases where you know broadside array and end-fire array. So in a non-isotropic sources, the first thing or the first case what you have is broadside array. How should be the pattern of a broadside array? Is it along the axis or perpendicular to the axis? Broadside array.
Perpendicular.
Yeah, it is perpendicular to the axis, which means that you have the patterns along this maximum directions. So this is the case where you considered same amplitude, same phase. Same phase means delta is equal to 0. So whenever the question is directly asked, broadside array, automatically it should come to your mind, the value of delta is 0 here. Clear? Always, broadside array, they will ask you the question directly, which means that the delta value is 0. So in a broadside array, the amplitude, the sources will have same amplitude as well as same phase. If we consider an array of 2 isotropic sources, now you have to apply it. Again here you have to find out what are the angles at which your main lobes are obtained, which is in the direction perpendicular to the array axis. So in order to find the field pattern, so the main thing in this case, what you do is you find the field pattern. To find the field pattern, you need 3 different things: peaks, nulls and side lobe direction. There you are finding maxima, minima, half power point direction. Here you will be finding the peaks direction, null direction, side lobe direction. So we know that phase angle, all the equations remain same almost. Beta d cos phi plus delta. You know the phase angle formula. It is xi is equal to beta d cos phi delta, where we know delta value is 0. So automatically our xi will be beta d cos phi. And here you consider, in case of non-isotropic sources, beta d is equal to dr, which is the direction, or we take, whenever you have beta, consider that as dr, just to make sure that you will not confuse with your case 1 and case 2. So beta d will take the form dr. So your xi will have the value dr cos phi. So this is the general equation of phase angle in case of non-isotropic array. Now trying to find out the direction, you have to find out first peaks. To find out the peaks, the step is you have to substitute xi is equal to 0. So if you substitute xi is equal to 0 to this equation, it will be 0 is equal to dr cos phi. You're finding peak, so I'll substitute the subscript as p. So now it will be dr cos p is equal to 0, where cos phi p is equal to 0. Phi p is equal to, what should be the actual peak's direction should be coming? Peak is nothing but this direction. Always it is broadside array. You must get it as 90 or minus 90 degree, or along with 90, 270. So those values only must come in a broadside array. So it is plus or minus cos inverse of 0. So what is plus or minus cos inverse of 0?
90, ma'am.
90 degree. But since we are deriving here the general equation, we'll write the general equation of cos 0, which we had taken there as 2n. So since I don't want you to get confused, I'll take it as k here, 2k plus 1 pi by 2. Follow the same thing, because or else you will be confused with those taking n there. Here you're taking again n. It will confuse your derivation. Non-isotropic, consider it as k. So it is 2k n plus 1 pi by 2, where your k will take the value 0, 1, 2, 3. Now consider if k is equal to 0. So phi peak will be equal to plus or minus pi by 2. So this is the peak direction what you're getting for a broadside array. So here direction of the maximum radiation is independent of number of elements, because how many number of elements if it is given, you will get the peak direction only towards the perpendicular direction here, because it's a broadside array. And till here it is fine. How to get the peaks? Because you have 4 cases, everything follows the same. And the problem also, you have to do it in this way itself. Clear?
Ma'am, can you repeat it once?
Yeah. Consider the case of broadside array. We know that broadside array is perpendicular to the axis. So you'll consider along the direction, that is with respect to 90 and minus 90, you have maximum direction. And we know that this broadside array is a case where the two isotropic point sources are having same amplitude and same phase, which means that the delta value will go to 0. So in the problems, they will give you certain parameters. Say, consider a broadside array with n is equal to 4, d is equal to lambda by 2. Draw the pattern. So in that time, you have to find out peak, null, and side lobe direction. To find out that, whenever it is given broadside array, take delta is equal to 0. And here you will be finding out the field pattern. So to find out this field pattern, you have to plot the peaks, nulls, and side lobe direction. Now, to find out that, we know the phase angle, that is I is equal to beta d cos phi plus delta. Delta is 0, so it will be beta d cos phi. So in order to reduce the confusion, we'll consider for non-isotropic sources, beta d is equal to dr. It is same, beta will take 2 pi by lambda, d will take lambda by 2. no change in any of the forms. But just to make sure no confusions, we'll just take it beta d as dr here. So xi will be dr cos phi. Here you'll be finding the first direction, that is peak. Peak direction is nothing but the one which your major lobe will define. That angle you will be finding. Substitute xi is equal to 0. This follows for all the cases. Whenever you have to find the peak for broadside array, you have to substitute xi is equal to 0. Substitute 0 here, it will be dr cos phi p. Cos phi p will be 0. Phi p will be plus or minus cos inverse of 0. General equation of that is plus or minus 2k plus 1 pi by 2, where k is equal to 0 will give you plus or minus pi by 2. But for the problematic purpose, you need to remember this equation, because based on the k values, you'll be going to find out what is the peak direction. So you'll get substitute 0, you get plus or minus pi by 2, which is satisfying your broadside array concept. Fine?
Yes, ma'am.
Okay. So moving on to the next direction, we have to find out what is side lobe. Side lobe direction. So to find out side lobe direction, you are using the linear array of isotropic antenna equation, which is electric field intensity sine n xi by 2 divided by sine xi by 2. So this value you will be considering, or this equation you will be considering. So in order to find out the side lobe direction, we need to equate the numerator of this equation to plus or minus 1, which means that the numerator is sine n xi by 2, which is equal to plus or minus 1. So again here it will be n xi by 2, which is equal to plus or minus sine inverse of plus or minus 1. What is the general equation of sine inverse of plus or minus 1? Then your sine will be plus or minus 1.
90 degree into 70.
Yeah. So you have to write the equation as plus or minus 2k plus 1 pi by 2. See, the main reason I'll not be taking n, because you already have n here. You will get confused if you take n here. So it is plus or minus 2k plus 1 pi by 2. Now simplify the equation. You have n xi by 2. I'll write in terms of xi. This 2 and this 2 gets cancelled. You have xi is equal to plus or minus 2k plus 1 into pi divided by n is the remaining equation. But we know that what is xi? Xi is dr cos phi. You're finding side lobe, so I'll write it as SL, which is equal to plus or minus 2k plus 1 into pi by n, where again here pi SL will be plus or minus cos inverse of plus or minus 2k plus 1 divided by n dr into pi. So this will be your side lobe general equation, which we'll be using for the formula, which will be used as a formula to find out the side lobe direction. K will again take the value 0, 1, 2, 3. So side lobe direction, when you compare, it is independent of size and direction of the beam area. We'll be considering directly the equation. Substitute for xi here, dr cos phi. Then write for phi SL, dr will come to the denominator, plus or minus cos inverse of this value. Clear? Is it okay? If
Yes, ma'am.
Yes, ma'am.
please ask me if you don't understand. Again, third direction is null's direction. To find out the null direction, you have to equate the numerator. Again, the same equation, sine n xi by 2 by sine xi by 2. What do you mean by null? Null is what? The value of null is usually we take. What we say null means? Null is when we use, sorry?
0, ma'am.
0. So what we do here is, in order to find the direction of nulls, we need to equate the numerator of this to 0. So you have n xi by 2, which is equal to plus or minus sine inverse of 0. What is the general equation of plus or minus sine inverse of 0? K pi. So whatever the values of sine, 1 pi, 2 pi, 3 pi will give you 0. So this will be xi is equal to plus or minus 2k pi by n, where we know again xi is dr cos phi. This is null. So I'll write the subscript as n, which is equal to plus or minus 2k pi by n, or it is phi n is equal to plus or minus cos inverse of plus or minus 2k pi by n dr. So this is the formula to find out the direction of nulls for a broadside array. Plus or minus cos inverse of 2k pi n dr. Clear till here? Write down this equation. You need to solve the problem based on this. Side lobe direction, maxima, that is peak direction, and the null direction. Clear the screen?
Just a minute, ma'am. Done, ma'am.
Okay. The next thing is, this is one formula which we need for solving the problem, that is first null beam width. To solve the first null beam width, you know the null equation, phi n is equal to plus or minus cos inverse of plus or minus 2k pi by n dr. To this equation, if we substitute k is equal to 1, or substitute k is equal to 1 in the equation of null, we get the first null direction. First null direction, which we consider as phi dash. So to this, I'm substituting k is equal to 1. You get it as phi dash is equal to plus or minus cos inverse of plus or minus 2 pi by n dr. So this is one equation. If we draw the broadside pattern, that is, we usually get the maximum direction like this. What is actually first null direction? We have done in the module 3. Half power beam width, first null beam width. What was actually first null beam width? Electric field will be 0, where your direction will come somewhere here. So this is actually a first null direction. Half power point will come on the major lobe. So I'll consider this first null direction as phi naught. Okay. So here phi naught is the first null beam width and phi dash is the first null direction. To find out the first null direction, that is from here to here, will give you first null direction. Half of that, which is phi dash. Now this will be from here to here, you know it is phi naught by 2. I'm considering from here, from the center, that is your first null direction, which is phi dash. Half of from this line to this line is phi naught by 2, because from here to here it is phi naught. Now seeing this figure, tell me what is phi naught by 2? This is 90 degree. Again, this you can consider as 90 degree. What is phi naught by 2? Or can I write it as 90 minus phi dash? Phi naught by 2. Yeah, 90 minus phi dash. So here, multiply that 2. So phi naught will be 180 minus 2 phi dash, where you know the phi dash value now. That is 180 minus 2 times of phi dash value is this. Substitute it here, plus or minus cos inverse of plus or minus 2 pi by NdR. Again, I can take 2 outside because I can again simplify this equation. Take 2 outside. You have 90 minus plus or minus cos inverse of plus or minus 2 pi by NdR. How can I write this 90 minus cos theta, or tell me what is 90 minus cos inverse of theta or 90 minus cos theta, anything is fine. You know that 0, pi by 2, pi, 3 pi by 2, 90 minus cos theta is what? You know this, right? All silver tea cups, all the values will be positive here. Sine, cos, anything. Here it is only sine. Here it is only tan. Here it is only cosine. So what is 90 minus cos theta?
Sin theta.
Sine theta. So here, and again, 90 is, if anything is divided for pi, then only your cos will be reversed to sine. If it is 90, sorry, pi minus something, it will not, suppose you have sine pi minus theta. There sine only remains, but you cannot change it to cos. Anything divided by 2 only changes to the alternative. So it is 90 minus cos theta is something is divided by 2. That is pi by 2. So pi by 2 minus cos theta will give you sine theta. So it is 2 sine inverse of theta will take the value plus or minus 2 pi by NdR. No need to worry about the derivation. Try to remember the formula, because formula is important here.
Ma'am, but cos 90 minus theta is equal to sin theta, no ma'am?
90 minus theta is equal to?
Cos 90 minus theta, ma'am.
Yeah, I'm taking it as cos now here. So it is 90 minus cos theta will give you the same value of sin theta.
Okay, ma'am.
See, it depends. The main thing is pi minus your theta value should come. Either it is sine or cos, or it doesn't depend, but you have a theta value, and this will satisfy your equation 90 minus this theta value. So the equation of first null beamwidth is phi naught is equal to 2 sine inverse plus or minus 2 pi by NdR. Note down this formula for first null direction. So a broadside array here, you will be having, you should remember, I'll clear the screen. You should remember actually in a broadside array, the first thing to solve the problem, delta is equal to 0, xi is equal to dr cos phi, and peak direction formula is plus or minus 2k plus 1 into pi, and phi side lobe is equal to plus or minus cos inverse of plus or minus 2k plus 1 into pi by NdR. Similarly, null direction is equal to plus or minus cos inverse of plus or minus 2k pi by NdR. And you have phi naught, which is equal to 2 sine inverse of plus or minus 2 pi by NdR. And the first null direction, what you got, that is phi dash is equal to plus or minus cos inverse of plus or minus 2 pi by NdR. And the last one, that is half power point direction or half power beam width, is nothing but phi naught by 2. So these are the formulas which you have to remember for broadside array. To solve the problem, you need to know all these equations. Here, Write down the question.
ma'am.
Yeah, we'll solve the problem tomorrow. Write down the question and keep. A linear array has 4 isotropic point sources. 4 isotropic point sources with separation between each source has lambda by 2. Delta is equal to 0. Obtain the field pattern. First null beamwidth. Obtain the field pattern. First null beamwidth and half power beamwidth.
Mom, can you repeat it?
Yeah. A linear antenna has 4 isotropic point sources. 4 isotropic point sources with separation between each source has lambda by 2 and delta is equal to 0. Obtain the field pattern. First null beamwidth and half power beamwidth. We'll continue it tomorrow.